My name is Muhammad Haris Haikal, and today I will be presenting about basic concepts in chemistry, which are atoms, molecule, ion, and chemical equation. First, I will explain about atom. An atom is the smallest unit of matter that still has the properties of an element. Atoms are made up of three particles, which are protons, neutrons, and electrons. Protons have positive charge, neutrons have no charge, and electrons have negative charge. The number of protons is important because it determines the element. The number of protons is important because it determines the element. For example, the hydrogen atom has one proton, zero neutron, and one electron, while an oxygen atom has eight protons, eight neutrons, and eight electrons. So, different elements have different number of particles. Next, I will explain about molecules. A molecule is formed when two or more atoms bond together chemically. The atoms can be the same elements or different elements. For example, oxygen molecule consists of two oxygen atoms, while water molecule consists of two hydrogen atoms and one oxygen atom. Now, let's move on to ions. An ion is an atom or molecule that has gained or lost electrons. When an atom loses electrons, it becomes a positive ion called a cation. When an atom gains electron, it becomes a negative ion called anion. For example, a sodium becomes Na plus after losing one electron, and chlorine becomes Cl minus after gaining one electron. Lastly, I will explain about chemical equation. The chemical equation is a symbolic representation of chemical reaction. It shows the reactant and product using chemical formulas. For example, in the combustion of hydrogen, hydrogen reacts with oxygen to form water. The reactant are hydrogen and oxygen, and the product is water. So for second subtopic is chemical nomenclature. What is chemical nomenclature? Chemical nomenclature is a system used to name chemical compounds. It helps to make sure the names are clear, systematic, and understood worldwide. The system is mainly governed by rules from IUPAC. Next, I will explain about naming ionic compounds. An ionic compound is formed from a metal and a non-metal. For the rules, the metal name stays the same, and the non-metal name ends with I. For example, NaCl is sodium chloride, and MgO is magnesium oxide. For transition metal, we use Roman numerals to show the oxidation state. For example, FeCl2 is named iron 2 Roman chloride, and CuO is named copper 2 Roman oxide. Now, let's move on to covalent compounds. Covalent compounds are formed between non-metals. We use prefixes like mono, di, tri, and tetra, and penta to show the number of atoms. For example, CO is carbon monoxide, CO2 is carbon dioxide, and N2O5 is dinitrogen pentoxide. Next, I will explain about naming acids. The name of an acid depends on the anion in the compound. If the anion ends with I, the acid name ends with hydroxy acid, such as hydrochloric acid. If the anion ends with it, the acid name ends with icy acid. For example, nitric acid. If the anion ends with ITE, the acid name ends with OUS acid, such as nitrous acid. Lastly, I will explain about bases and hydrates. Bases usually consist of a metal and the hydroxide ion, OH minus. For example, NaOH is sodium hydroxide, and CaOH2 is a calcium hydroxide. Hydrates are written as a compound followed by water molecules. For example, CuSO4 5H2O is called copper 2 Roman sulfate pentahydrate.
Mole concept and angular number. So what is an atomic mass? Atomic mass is an atom of an element compared with that one atom of 12C. So by definitions, we get one atom of 12C weight 12 mol. So relative atom mass, meaning the weight average of all natural occurring isotope in an element. So you can find it on the periodic table, but we take as example C. The above number of C is the atomic number. Below is atomic mass. So next, we talk about natural occurring. Natural occurring, for example, we take lithium, the percentage, and the MO. To calculate atomic mass based on lithium, we take the percentage multiplied by the MO plus both of them and over 100, so we get 6.941 MO. So moles is we talk about moles. Mole is the amount of substance that contain many elementary entities. There are atoms exactly 12 grams of 12C. So Avogadro number, we got 1 mole equal to Na equal to 6.0022127 multiplied by 10 power of 30. That number is constant. So you can see on the slide 12, which is like the table of the number of equals. So next, we talk about molar mass. Molar mass is the mass of 1 mole in a gram. So if 12C atom equal to 12 MO. Okay, MO is equal to gram both in molar. Intercommenting mass, mole and number of particles. So to convert it gram to moles, we use molar mass. Moles to formula unit, we use Avogadro number. So moles provide a path to the small molecular scale to the real time scale. So in mole concept, we use triangle concept. So the first triangle concept is mass over moles multiplied by RMM or RAM. So next, the second triangle is number of atom over moles multiplied by Avogadro number. So what is formula mass? Formula mass is the sum of atomic mass in MU in a formula unit of ionic compound. 1 unit NaCl equal to 58.44 MO. So 1 mole NaCl equal to 58.44 g gram NaCl. So in the simple term, formula mass is equal of Mu equal to molar mass of gram.
Today, I will be presenting about empirical formula and molecular formula. First, I will explain about empirical formula. An empirical formula shows the simplest whole number ratio of atoms in a compound. It does not show the actual number of atoms, only the ratio between them. Usually, empirical formulas are determined from experimental data, such as percent composition or mass data. For example, the actual formula of hydrogen peroxide is H2O2, but the empirical formula is HO. Another example is glucose. The actual formula is C6H12O6, but the empirical formula is CH2O. For benzene, the actual formula is C6H6, and the empirical formula is CH. Next, I will explain about a molecular formula. A molecular formula shows the actual number of each atom in a molecule. The molecular formula is always a whole number, multiple of the empirical formula. To determine the molecular formula, the molar mass is required. The relationship between empirical formula and molecular formula can be shown using this formula. Molecular formula equals n times empirical formula, where n is the molar mass of the compound divided by the molar mass of the empirical formula. For example, if the empirical formula is CH2O, the molar mass of the empirical formula is 30 grams per mole. If the actual molar mass of the compound is 180 grams per mole, the value of n is 6. Therefore, the molecular formula is C6H12O6. That's all from me. Thank you for your attention.
Assalamualaikum and hi everyone. So today I will be teaching you guys about percent composition and balancing chemical equation for Chemistry 131 Chapter 1. Okay, so there are two subtopics that I will be teaching for today. Okay, so let's jump to the first subtopic. The first subtopic that I will be teaching you guys is percent composition. So what is percent composition? Percent composition is the percent by mass of each element the compound contains. Okay, so here is the formula for the percent composition. So there are N times molar mass of element divided by molar mass of compound and times 100%. Okay, so what are the N? N is the number of mole of the element in 1 mole of compound. So as an example, there are 1 mole of NH and there are, so like this, there are 1 mole of NH and there are 2 on the subscript. So this subscript indicates the value of N. Okay, so without further ado, let's jump to the question. So here are one of the question for percent composition. So it's stated here, aspirin is a compound with the molecular formula of C9H8 and O4. What is its percent composition? Okay, so I have already determined the molar mass of the compound is 180.15 gram per mole. Okay, so we start with the element C. So the element C have 9 subscript on it. the subscript is the letter F. After the letter 9, after the letter C, it has a small number which is 9. So that is the n value, remember? So we just sub in into the formula. So the formula said that the n will be, so for C9 equals to 9 times the molar mass of C. The molar mass of C is 12.01 gram per mole divided by the molar mass for compound, which is 180.15 gram per mole times 100%. Okay, so as simple as this, we can determine the percent composition for this specific element. So we put the value in our calculator, make sure it correct. We doesn't miss any of the value. 180.125 times 100. Okay, as you can see here, sorry if it's a mirror because I use the front camera. So we get 60. Wait, I think there's a bit, oh, okay, it is 60. So for C percent is equals to 60% of C. Okay, so let's take a look at the H and for the O. I just use the same technique, which is N, which is the subscript, and times with the particular molar mass of the element divided by the compound, the molar mass of the compound, and times with 100%. So here for the H percent, I got 4.476% for hydrogen, and for the oxygen I get 35.52. So that's all for the percent composition. Make sure to do a lot of exercise to get better at chemistry. So let's move on to the balancing chemical equation. So we are moving on to balancing chemical equation. So for the balancing chemical equation, there are four main or the key components to make the chemical equation balanced. So let's check it out. So the first one is write the correct formula for the reactants on the left side and the correct formula for the product on the right side of the equation. Number 2, change the number in front of the formula, which is coefficient, to make the number of atoms of each element the same on both sides of the equation. Do not change the subscript. Okay, so let's differentiate what is coefficient and the subscript. So okay, the subscript is this little number after the element, which is like this, H2O. So the subscript number for H is 2. That is the subscript. So the coefficient means the number before the element, and the number we will write it down with a big letter like this. So take a look for sodium and A here, I put 2 as the coefficient. So that is the difference between the subscript and the coefficient. So we cannot change the subscript value, but only the coefficient value to balance our chemical equation. Okay. Next rule is start by balancing those elements that appear in only one reactant and one product. And lastly, check to make sure that you have the same number of each type of atom on both sides of the equation. Okay, without further ado, let's make an example for this chemical equation subtopic. Okay, so here I have already a chemical equation, but it is not balanced yet. So firstly, I have differentiate the reactants and the product. So the left side is the product, the right side is the product, and the reactants are on the left. Okay, so first we need to list out how many number of atoms for each element in the reactant. Okay, so we list out first. For Na we have only 1. For hydrogen we have 2 because the subscript is 2. So we have 2 hydrogen here and only 1 oxygen. Only 1 oxygen. So for the product we also have 1 Na, 1 oxygen, 1 hydrogen, but we have plus hydrogen with the subscript of 2, so it means we must add 2. So the total on the product for hydrogen, number of atom for hydrogen at the product is 3. Okay, so there's a big problem because the hydrogen is not balanced. So how can we balance? By putting a number of or value at the coefficient. So how? So we can put 2 H2O on the reactants. So that is 4 number of atoms for hydrogen on the reactants, and we can put this 2 coefficient for the product at NaOH. So there are 2 hydrogen 2 hydrogen plus 2. Is it correct? Yes, it is correct. So it becomes 4. So here the hydrogen is already balanced, but if we look closely at the compound, the H2O, so it means the coefficient will multiply the oxygen, right? So the O for the reactants becomes 2, and O on the product is also 2. And lastly, we check on Na. Na at the product is 2, and Na on the reactants must also 2. So we put simply coefficient 2 on Na. So it is already balanced. Okay, so that's all from me. Thank you.
We talk about reaction yield. So reaction yield is the measure of efficiency of any chemical reaction. So in a simple term, it's compare the amount of product that actually obtained and what we should have obtained in the experiment. So we use it based on stoichiometry. So first we got two yield. First the theoretical yield, and second is the actual yield. What is theoretical yield? Theoretical yield is the amount of product that should be result if all the limiting reagent reacted. So actual yield was the amount that we get on the experiment. So in a simple term, how to calculate? So to calculate the yield, we need to use an equation. Percentage of yield equal to actual yield per theoretical yield equal multiplied by 100%. So we need to remember the actual yield never exceeds the theoretical yield. So in the simple term, the what we obtain should be never exceeds the what we should have obtained. So for example, we take example, 0.8 gram of copper should be produced, but only the student make only 0.77 gram. So what happened here? So we need to calculate what is the percentage. We use the same formula. So we got 0.77 gram per 0.8 gram multiplied by 100. We got 96.225 percentage. That was the reaction yield.
Hello, I am Muhammad Nazmi bin Ismail. So I will be presenting stoichiometry calculation. So stoichiometry is basically often considered as the math of chemistry because it involves using the relationship between reactants and products in a chemical reaction to determine desired quantitative data. So let's see the procedure. First, we need to balancing the equation. You cannot do stoichiometry without a balanced equation. This satisfies the law of conservation of mass. Second, we convert it to moles and to find the mole ratio. Because the mole ratio is the conversion factor that allows you to jump from one substance to another in a reaction. And then the final step is to convert it to final units. In stoichiometry, we also have limited and excess reactant. The limited reactant is the region that is completely consumed. It determines the maximum amount of product formed. And how to find it? We just need to calculate the amount of product formed by each reactant separately. The one that produces the smaller amount of product is considered as limiting reactant. And for excess reactant is the substance that remain after the reaction stops. I will explain it more about limited and excess reactant later. Don't worry. Next, we have percent yield. So percent yield is to find theoretical yield, which is the maximum amount of product calculated on paper, and actual yield, which is the amount you actually measure in the lab. There's also a formula to find it, which is actual yield per theoretical yield times 100%. And lastly is common pitfall to avoid. Yes, which is first, don't forget to balance seeing the equation, right? It is very important because if you didn't balance it or maybe balance it wrongly, it will ruin the whole calculation. Second is sig fix, and the lastly is units. Don't forget or use the wrong units. All right, so let's move to the next topic, which is limited reactant. In chemical reactions, reactants are often not present in the exact proportion required by the balance equation. This leads to the concepts of limiting and excess reactants. So limiting reactant, the definition of it is a reactant that is completely consumed first in a chemical reaction. It limits the amount of product that can be formed, uh, and while once it is gone, the reaction will stop. The excess reactant is the reactant that remains after the limiting reactant is completely used up. There is more of it than needed to react with the limited reactant. And then we also have a formula here on how to determine a limited reactant. There are a couple of formula actually, but this is one of it. We also have ways to calculating the amount of excess leftover. Once you know which reactant is limiting, you can find out how much of the excess reactant remains. So first step, we need to use the moles of the limiting reactant to calculate how many moles of the excess reactant that are actually consumed. Need to use the mole ratios. Then we subtract the consumed moles from the initial moles to start with. Third, we convert the remaining moles back to grams if required. And here's a quick tips. Always use the always use the limiting reactant for any further calculations, like finding the amount of product or excess use. Using the excess reactant will give you a theoretically impossible answer. Right? That's all from me for stoichiometry and limited and excess reactant. Thank you.